Right, we are going to look at the knowledge area mechanics. What do we mean by mechanics? Right, mechanics is actually a branch that deals with kinematics and dynamics. Kinematics uh, comes from the word kine, meaning motion, and in kinematics, uh, it describes the motion without regard to its cause. That means in kinematics, you're just looking at the motion and you're not really worried about what's causing the motion. In dynamics, it describes the motion and the relationship of the motion to force and mass. Right? So in dynamics, you're looking at motion and you're looking at the forces that affect motion. Now, dynamics, you're going to be doing in grade 11 when you do Newton's laws, right? But at this point, we're only going to look at kinematics. So, in kinematics, the focus that we are going to have is on one-dimensional motion, right? That is motion along a straight line. And we will look at motion along a coordinate axis. So let's say, for instance, we have an axis here, and that's our x-axis, right? So we're going to look at motion along a coordinate line. It could be an x-coordinate line. That means your object or your particle moves along this coordinate line. Right, and it could either be moving in that direction, right, or it could be moving in that direction. So motion along a line can only be in two directions. It needs one coordinate to specify its position. Right, so if you have an object moving along a line, it could be moving towards the left or it could be moving towards the right. But we can choose the direction we want. If it's moving towards the left, we could say moving towards the left, the direction is negative, and if it's moving towards the right, we can say the direction is positive. Or we could say it's moving towards the left or it's moving towards the right, because that's the only motion the object or particle can have along one-dimensional line that I've drawn here. Or alternatively, we could also have an object moving up or down, right, along the y-axis. Right, the motion is along the line, and it could be going up, right? It could be up, or the motion along that line could be down. Okay, but sometimes, I mean, if we want to, we could say the up direction is positive and the down direction is negative. What we could choose that direction. Right. Now, we will study motion only in one dimensional space. We will not be doing anything in 2D or 3D, right? What I mean by that is, say, we have here a y and an x, right? And we have an object or a particle here in this space. It will have an x coordinate and a y coordinate, right? It's given by two space coordinates. So we're not going to be looking at anything in 2D, right? So no 2D motion or motion in a plane. We're just looking at motion in a straight line. It could either go up, down, right? Right. Now let's look at the physical quantities, right? Some of the things we measure are determined simply by magnitude only, right? And other things need to be described by direction and magnitude. Right, so here we have a vector quantity. A vector quantity that has magnitude and direction. Okay, so a vector quantity has magnitude and direction. Right, and because we're dealing with a physical quantity has a unit as well. Right, now there are several vector quantities here which I will draw your attention to, and take note because we will be using these quantities as we progress and in subsequent lessons. So the physical quantity displacement, its unit, what's its unit? Its unit is meter or kilometer, right, or centimeter. So that's the displacement. But in addition to the unit, it must have a direction, right? And from where it is, we could say it is in an easterly direction, or it's in a westerly direction, or a northerly direction, or we can choose direction towards the right as positive, then we say in a positive direction. Velocity, the unit of velocity is meters per second, right? How many meters are covered in a second? Or we could also write it as meter s minus 1. Acceleration and velocity is also a vector quantity. Acceleration is an indication of how fast the velocity is changing per unit time. So in that case, it will be how fast the velocity is changing over time, and we write that as m per second squared, meter per second squared. Right. And force, you have dealt with this already. The unit of force is a Newton. Okay? And that also has direction because the force has to be exerted in a specific direction. And then weight is also a force with which the earth attracts an object, and it moves, the force is towards the earth, and that is also in newtons. Right, so those are vector quantities, and all of these require direction, right, in order to specify them. And also when we are going to use rules to add vectors, we will need to take direction into account. Unlike vectors, we have a scalar quantity. A scalar quantity has magnitude only, like mass, right? Mass has magnitude only, but we obviously give it a unit, so we know if we're dealing with the unit, so we say unit 2 kilogram, so the magnitude would be 2, so it's 2 kilogram, so the unit is actually kilogram. Temperature, we know, is degrees Celsius, right? Or it could be Kelvin. We, in these cases, we are not worried about the direction. If we have a mass of 2 kg plus a mass of 3 kg, the total mass would be 5 kg. We don't say it's 5 kg, 5 kilograms east or 5 kilograms north. Likewise with temperature, if we add the temperature, 20 degrees Celsius plus 30 degrees Celsius gives us 50 degrees Celsius, and it can be specified without giving a direction. Distance is in meters, right? But it doesn't require a direction. Unlike displacement also has the unit meter, but we need to know where it is from a particular point. A distance can be anywhere from from a focal point. Speed is meter upon a second, or we write it as meter per second. And when we're dealing with speed as well, speed does not have any direction. It's a scalar quantity, but velocity needs to have direction. Work, and what's the unit of work? It is a joule, right? And work is energy transferred to a system, and the energy transferred to a system is not dependent on direction. Time we know is measured in seconds or hours, and time again does not have any direction. We don't say it is 3 seconds east or it's 4 seconds west, right? We just add the magnitudes. Right, now let's look at representation of a vector quantity example. The length of the line, right? The length of the line represents the magnitude, okay, of the vector, while the arrow represents the direction of the vector. Right, now we will use force which is a vector quantity, as I have shown you. We will use force as a vector quantity. Now let's look, let's say for instance we have a force, right? There's a force, and let's say we could draw this to scale, but I won't be drawing it to scale. So let's say for instance we have a force of, let's say, 20 newtons, right? And it's 20 newtons, okay, and it's moving towards the right. So we could say it's moving towards the right, or we could take the movement towards the right as positive, right? That force is towards the right as positive, and we could say the force moving in the opposite direction is negative. Okay, so that choice is arbitrary. Okay, we could either way, the positive could be in the forward direction and the negative in the direction towards the left. Right, but now this is your vector, and that is your starting point, and that's your arrow, right? So thus we normally say it is the tail of the vector. Okay, that's the tail of the vector. This here is the arrow, right? And sometimes you also call this the tip or the head of the arrow, right? So a vector is specified. So if it's going to the right, we could say plus 20 newtons, and the length of the arrow gives you an indication of the magnitude. Okay, and if we drew this to scale, and we said 1 centimeter is equal to 1 newton, then we would have had to have a 20 centimeter line, and if it was going in a positive direction, then we need to specify that. Right, we could also say this is force is towards the right, and if it's towards the right, And if we chose the direction as positive, then the force is plus 20 newtons. Right. If we had the same force with the same magnitude, and we have that, and that's my starting point, this is my arrow here, right? And here, if it's the same magnitude, that means the length has to be the same, right? Only thing is the direction is different, so this here would be minus 20 newtons. So remember that and that together here, the signs indicate direction. That is important. Right. Negative doesn't mean it is less. Right. Negative just means that it's in a opposite direction. It's equal in magnitude, but in the opposite direction to the plus 20 newtons. Right. Now let's look at force acting up or down. Here we got a spring balance, and a spring balance normally measures force, right? It's calibrated in newtons. So if we have now looking at here a particular object, 10 kg, and suspended from the spring balance here, right? And as you can see, I mean here, let's assume it's stationary and it's right. And if we look at this 10 kg, and we look at the force, so we say, okay, there's a force acting downwards, right? That's because we have the earth here. Earth exerts a force on that mass in a downward direction. And what happens? You have your spring, right? That's exerting a force in the upward direction. And what's the force? If we read it off here, it's about 100 newtons downward direction and 100 newtons in a upward direction, right? So we need to say 100 newtons upwards or 100 newtons downwards. But if we choose to use plus and minus, we can say that if it's going up, it is plus 100 newtons, and if it's going down, it's minus 100 newtons. So which essentially means we're taking the up direction as positive and the down direction as negative. Right, we could have chose the up as negative and the down as positive. Right. So now we see forces acting left or right. Now here we have Umpo exerting a force on a table, right? And if we look at the force that's being exerted on the table, here we could say it's moving towards the left, or we could say that the force is minus 100 newtons, meaning that we're taking the left direction as negative and the right direction as positive. So that would be 100 newtons. Right. So we have that, and here, as you can see, is drawn, they sort of equal in magnitude, right? Okay. Now let's look at the next one. What do we have here? Here we got a spring balance again, but it's actually pulling a block of wood, right? So a spring balance that's pulling wood, right? And if we look at the spring balance here, what it's showing is showing 4, and if it's calibrated in newtons, as you can see there. So if I look at this block, right, and we want to know there's a force moving in that direction of 4 newtons. So we can say it is 4 newtons to the left, or if we want to, we say 4 newtons negative, which means that direction we choosing it as negative. Had we chosen that direction as positive, then that would be 4 newtons positive. Right. Now, if we're looking at representation of directions of vectors, now we know a vector direction can be represented in several ways. Let's look at a few ways. Right. The one is up, down, left or right. So we could say, for instance, we have, let's say, an object here. Let's assume it's an object at that point, and then we have a force in that direction and a force in this direction. So we could say it's up and that is down. Or let's say we want to say 10 newtons, right? And we could say 10 newtons if we're taking the up direction as positive and the down direction as negative, then that would be plus 10 and that would be minus 10. Right. And let's say, for instance, we're looking at left and right. So here we have an object that's pulled that way and there. So let's say from this point we have an object here, right? And it could be a force in that direction, right, of 20 newtons, or it could be in that direction of 20 newtons. But if I'm taking that as positive, then that would be positive 20 newtons, and that would be negative 20 newtons. Right. Okay, now let's look at reference to a fixed point. Right. Here, for instance, we could have, let's say, a rubber bank. We have a rubber bank. So we have a rubber bank. Right? And here, since we're looking at a fixed position, it could be a rubber bank, it could be a building, it could be any other fixed position that we using to measure the angle. And here in this case, so let's say we have for instance at the rubber bank, and we may have an ocean current moving in this direction, right? And this ocean current may be at an angle of 30 degrees to the rubber bank. And the ocean current could have maybe a velocity of, let's say, 5 meters per second, right? And it's giving us a direction in which direction it is moving, right? And let's say it's a velocity, and velocity is a vector, okay? Now let's look at reference to compass points. Here we can have, for instance, that is north, that is east, that is south, and that is west, right? If we now have, let's say, a vector in that direction, and let's say that is now 40 degrees, right? So it's 40 degrees, actually 40 degrees going towards the north of west, right? So it's moving in that direction. That's your north. Right, and it could be, for instance, wind blowing with a force of 50 newtons. Right, or it could even be wind speed in meters per second if that speed is a velocity, if that velocity is directional. Then bearings. If we're looking at bearing now, bearing, we start with 0 degrees, 90 degrees, 180 degrees, and 270 degrees, right? When we measure bearing, we need to measure it. We need to measure it along along the axis here. So, for instance, if we have it's 115 degrees. So when we measure it, we start with 0 degrees here, and it's measured clockwise. So we know that is 90, and 115 would be slightly somewhere there, and that would be 115 degrees. When we say on a bearing of 115 degrees, we mean that it's measured clockwise, right? And not anti-clockwise. Okay? Right now, we look at a description of a resultant vector, right? So before we go to the description of a resultant vector, let's, for instance, look at what we mean by that. Here I've got a demonstration for you, and you see I have my red team and I have my blue team, right? And then we have a trolley. Okay, so what we're going to do is you can see that it says force to the right, but I will just get its value, and its value is 50 newtons to the right. And if it's 50 newtons to the right, and if I want to know what is the net force on this and in which direction it moves, see, that tells me the sum of the forces. There's only one force, so the sum of the force is towards the right. And if I do that, see what happens. It moves towards the right, because the net force is in that direction. Okay, now let's, for instance, say I have one on this side. Then you can see we got a force on the left of 50 newtons and force on the right of 50 newtons. So what is the sum? The sum is 0, right? So in which direction is this going to move? We say go, and we find that it doesn't move in either direction because the forces are balanced. Okay, now let's say, for instance, we add another force here. So you can see the red team, they have 150 newtons towards the right, and the blue team has 50 newtons towards the right, towards the left. And we want to know, and according to this, the sum of the forces is 100 newtons, and that force is towards the right. Let's just put the speedometer here, just to check what the speed is, and we say go, and it's moving. See what's happening to the speed, it's also increasing. Right, so red wins. Right, and then we go and we say, okay, let's see if we can increase. So now it's both 150 and the sum of the forces is 0. Let's add one more. And here we have now towards the left is 300 newtons, towards the right is 150 newtons. Look at the sum of the forces. That means the sum or the resultant force, or the resultant force of these two opposing forces is a force that moves, is a force in the direction towards the left, right? And if we do that, right, so there you have that, okay? Right, now let's go and look at this, the description of a resultant vector. Firstly, a resultant vector is a single vector that has the same effect of all the component vectors together, right? Right, and here we say the sum or resultant vector, right, is the arrow drawn from the tail of the first vector, right, to the tip of the last vector, right? So from the tail, right, of the first to the tip of the last vector. Okay. Right, now let's look at this. Here we got forces are balanced. In this situation, the forces are balanced, and let's have a look at it. Here we got 150 newtons towards the left, and we got 150 newtons to the right. So what happens? The sum of these forces is equal to 0, right? In this case, so they are balanced. Now, if we look at if we look at this, and let's say for instance we want to know what the resultant is, we say, right, we have this. So if we're looking at this, we say, right, we could take that as positive and that as a negative direction. And if we want to know what the resultant is, what do? We could use let's say, right, we want to know what the resultant is. So let's say the resultant, right, but let's do the resultant first geometrically, right? So geometrically, let's show it geometrically, okay? Geometrically, right. What do? We have our vector moving in that direction, and that is plus 150 newtons to the right. Right. So we know that there is our tail, and that there is our head. Right. So we've represented this. Now we need to represent that, and in terms of the rule we had, So we take the tail of this, right, the tail of that, and bring it there, and that is minus 150 newtons. So what is the resultant? The resultant in this case is equal to 0, isn't it? Because when we add these vectors successively, the resultant is that the force is back to where it originally was. So that's your first vector, and that's your last vector, and there is no difference between the distances of the tail and the head of the last vector. Right, that's geometrically done. But if we now want to show this algebraically, we would say that algebraically, right, we're using algebra. So if we use algebra, right, or algebra, which would then mean, so let's say for instance, we want to know the resultant force. Right, so let's say if I want to know the resultant would be, in this case, plus 150 plus 150 plus 150 to the right, plus minus 150 to the left, and what does it give us? 0 newtons. Okay, and which is concurs with this. Okay, so the resultant is 0. Let's look at the next one. So here we have now 300 newtons to the right and minus 150 newtons to the left. And what does it tell us? It says that the resultant or the net force is 150 newtons to the right. Now, if we sort that out geometrically, we could then let's just do this, right? So let I have a bit more space. Right. So if we're doing it geometrically, we could take our force. So we start at that point. So we say, all right, let's say I have 150. Now I have 300 newtons this way, right? And then I have, so that's my tail, isn't it? And that's my head. So that's my first vector. Now I need to represent that vector. So that one goes halfway. Well, that doesn't seem totally halfway, but that goes halfway there. And so that's my head, and here again my tail, right, to there. And what's the resultant? The resultant vector is right, that's the resultant vector, and that is 150 newtons, because your tail is there and your head is there, and that is 150 in a plus direction. Remember, this here was minus 150 newtons. Right, so that's done geometrically. Okay, but if we are looking at this in terms of algebra, then we're going to say the resultant or the net force resultant is equal to plus 300, right, newtons plus 150 in the opposite direction, and that gives us plus 150 newtons. Right, that's when we do it algebraically and we take the one direction as positive and the other one as negative. Now let's look at the next one. Here we have a force of 150 newtons, and this side we have a force of 300 newtons. And this tells us that we're going to have a resultant force towards the left. Right, so if we look at this now geometrically, we could now say, okay, I have this particular, we could even call this, even if we call this, we could label it, but so let's say geometrically I start with this force. Right, I start with this force, and that force is now, I'm moving towards the right, and that is plus 150 newtons, right? So that's my tail, and that's my tail, and that's my head. Now I have to represent this, so I do the same thing. I start with the tail, where my head, I then start with my tail, and we go in that direction, like that, and that is a 300 newtons, and it's in a negative direction. Right, so what is the resultant? The resultant is actually from the tail of the first to the head of the last, and that is my resultant, which then is equal to 150 newtons, and in a negative direction, which is what we have here. Right. So I chose that. But let's say if we decided to, instead of having moving from to the right, we could have even done this first. We could move 150. We could have moved 300 to the left, right? 300 newtons to the left. So that's my tail and that's my head. Then I need to represent this particular vector which is moving in the opposite direction. So we have that, and I go there, and that would be 150 newtons positive, correct? So there's my tail, there's my head. So there's my tail and there's my head, which shows that this resultant, right, or the sum is pointing leftwards, which means it's minus 150 newtons. Right, minus 150 newtons. Right, that's geometrically. But if I want to do it in terms of algebra, I would have then said I take 150. So my resultant would be 150 newtons to the right, plus it would be minus 300 newtons to the left, and which means it would be minus 150 newtons. Okay. Right. Now let's look at the exercise here. Right. let's look at the exercise. Here we got what is the resultant force in the first and second picture. Okay, so let's say we take that as being positive and that as being negative. Then if we did this geometrically, it would mean I have one moving in that direction as 300 newtons in the plus direction, and thus will then move in the opposite direction, right, of minus 300 newtons, and the resultant here is equal to 0 because it's back from where the first vector originally started, right? And algebraically, if we want to, we could even say, okay, let's say resultant is equal to 300 newtons in the plus direction plus 300 in the minus direction, so that it gives us 0 newtons. Right, let's look at the next one. Here you got 300 in that direction and 400 in that direction, and if we look at this geometrically, we could have 300 plus 300 in that direction, and then the other one is 400 newtons in that direction. So what is our resultant? Our resultant would be from there to where it is, and that would then be 100 newtons to the left. Right. So, and algebraically, so we could even say resultant is equal to 300 newtons plus, right, the other one going in the opposite direction, and that gives us minus 100 newtons. Okay, now let's look at the next one, which says, right, it says give the direction of the vectors A, B, C, D in two different ways. The one way is represented like 50 degrees north of east, and the other one represented as a bearing. Okay? So A would be, if we look at A, that would be 30 degrees east, right, of north. And what would its bearing be? That would be its bearing, and we can say on a bearing of 30 degrees, right? Let's look at B. B is 50 degrees, right, south of west. Right, so I'm not going to keep on writing on a bearing of, so you need to say on a bearing of, and that would be B would be on a bearing of, that's 90 plus 50. If we're looking at it in terms of bearing, that would be, because remember with bearing, we start with north there, and that's 90, and that's 180, right? And that's 270 there. Right, so that would be, in this case, it would be from there to there, which means it would be on a bearing of 140 degrees. C, that in terms of the compass, we would say 70 degrees. 70 degrees is going west, but of which side? West of south, right? Because we know that's our south. And what is the bearing? The bearing would be 90, 180, and that would be on a bearing of 250 degrees, right? So you need to say on a bearing of, right? Then we know how we're measuring it. We're measuring it clockwise. And then here we got 25 degrees, so it's 25 degrees north of west, right? So what would it be? 180, 270, and 25, that gives me 295 degrees. Okay. Right? Now look at which of the following physical quantities are vector or scalar quantities. Give the units of each. Alright, so we got distance. Distance is a scalar quantity, right? And the unit of distance is a meter, and we know it doesn't require any direction. Displacement is a vector quantity. It's also measured in meters or kilometers, but it's also measured in kilometers. Meters or kilometers, but when we're dealing with vectors, we must have plus, it must have a direction. Okay? Speed is a scalar, and the unit of speed is meter per second, or I could write it like that, and there's no direction. Velocity is a vector, and it's measured in meters per second or meter s minus 1. Then we say plus a direction. Acceleration is also a vector quantity, which we will be dealing in subsequent lessons. And the unit of it is meter. It's meter upon a second per second, and which I write as meter per second squared, right? And that's plus direction. Okay, that's plus direction. Right, there you have it. And see you next time.